Okay, why for Gauss law? Gauss law is a very convenient tool to compute the electric field and the electric field flux in case that there is a symmetry. I have included additional figure in comparison with the previous version to help you understand the situation better. We have a plane. On the plane, there is a sphere of a radius a. And we have rotated this plane about the y-axis passing through the bottom point by an angle theta. And you will find the cross-sectional area x appears in here. If I make a cross-section perpendicular to this cross-sectional view shows a circle, and this is a radius a from the bottom. This is also a from the bottom to the center of the sphere. Because this line has been rotated from this line by an angle theta, this plane that makes the cross-sectional area x is shown as a straight line. And normal vector n hat is perpendicular to this line. Now the situation is understood much better. So this is an angle, this is a right angle. This should be 1/2 pi minus theta. Therefore, this guy is theta. Then the perpendicular distance from the center to this line, to this plane, this red plane, is a cosine theta. This is a right triangle, so this side is a sine theta. Now we are ready to solve the problem. Electric field flux passing SR. SR is on the right side. So there is a cross-sectional area X. Electric field is passing in here. Whatever shape of surface whose boundary shares with the cross-sectional area X, the electric field flux is the same. The reason is that divergence E is rho over epsilon 0, coming from the last problem we learned yesterday. This divergence E integrated over some volume, according to the divergence theorem, must be the same as the surface integral, whose surface is the boundary of this volume. The problem is that there is no charge distribution inside the sphere. Therefore, rho equals 0. So the integral, volume integral on the left-hand side is exactly 0. And this is a closed surface. So electric field flux integrate over a closed surface is exactly 0. But this closed surface consists of this surface and this cross-sectional area with the direction opposite. Because the sum is 0, this flux A and this flux B, the sum of these must be 0. Okay? That's the reason why flux passing in this way and flux passing in this way, whenever they share the boundary, the shape doesn't matter. The value of the flux passing this surface or this surface, they are the same, identical to each other. That is the crucial point of Gauss' law. SL is the left-hand side, and the SL, whose normal direction is toward outside of the sphere. X has the normal direction this side. So these two share the same boundary, but the direction is opposite. Therefore, the flux is the same, except that we have negative sign on it. Flux passing the whole spherical surface, union of left-hand side and right-hand side. This is a closed surface. Closed surface. Closed surface. It should be zero because it is empty. No electric charge inside. This is the summary of what we have discussed until now. Using these basic principles of Gauss' law, we solved the problem 2, the same problem. Radius r of the circular cross-sectional area, this radius r, and what is r? This is r sine theta. Perpendicular distance from in here, we calculated. It is our a cosine theta. The electric field flux passing x with normal vector n hat. That is the area of this cross-sectional area, and this area vector carries the unit vector n hat and electric field. N hat and E1, their angle is n hat at E1. That angle is 1/2 of pi minus theta, so that is sine theta. As a result, because r is a sine theta and n hat at E1, because E equals E0, E1 hat, so this scalar product brings in sine theta, and radius r squared brings in a squared sine theta. So we have original circular area, cross-sectional area of a large circle of the sphere multiplied by the electric field, but we have additional factor of sine cubic theta. Next, this is a very nice demonstration of computing the electric field flux. We have a charge Q at the center of the sphere. This plane passes through this axis, so it determines azimuthal angle phi. And you find there is a cone. This curved surface is a part of a cone with an angle with respect to z that is polar angle theta. We know that the electric field coming out of a single charge everywhere, electric field flux, according to Gauss' law, is a charge divided by epsilon 0. In here, it is a hemisphere just cut it into two pieces. So the whole surface, we have 1/2 factor 2 in the denominator instead of Q over epsilon 0. And once you are given a surface, in this problem, radius doesn't matter. In here, you find radius cancels. Only the solid angle is concerned. Just to bring out the overall coefficients, and this one is a 4 pi when it is being integrated over the whole solid angle. To find 4 pi cancels to get Q over epsilon 0 in case we have integrated over the whole space. If you integrate over the semi hemisphere, it is Q over 2 epsilon 0. Now, A, B, C, D contribution can be evaluated by substituting the lower limit and upper limit for the integral. And these are the results. Okay, we have Q over 4 pi epsilon 0 factor missing in here. This is page 5, Q over 4 pi epsilon 0 D. So you need to include this Q over 4 pi epsilon 0 in here. This one is wrong. So if you add these 4 contributions, you will find the answer is Q over 2 epsilon 0. Next, we have a charge Q distributed over a disk, and this disk fits this surface. What is the electric flux passing A, B, and C? Because we have a common boundary, everything has the contribution Q over epsilon 0, but on the left side, right side, sum is this. Therefore, because of symmetry, passing A, B, C are all Q over 2 epsilon 0. This is a trivial problem, but it looks very complicated. It makes use of the Gauss law in a clever way. So everything has the same result. Number 5, imaginary spherical Gaussian surface S of radius r is passing a square that barely encloses the cross-section of the sphere. Evaluate the electric field flux in the stages A, B, C, and D. Okay. A, this sphere does not touch. So over the sphere, there is no rho inside, right? So divergence E equals 0. That means E dot this sigma is 0 for the any closed surface. That is the boundary of volume that does not contain any electric charge. So we have this one, this one, this one, no charge inside. So they are trivial, 0, 0, 0. Only in this case, we have a non-vanishing contribution. And this one, we have charge inside. And we have divergence E equals rho over epsilon 0. Its a volume integral is a charge over epsilon 0, right? So the electric field flux should be charge over epsilon 0. What is the charge? Okay, inside the sphere, we have uniform charge distribution sigma, and the area of this disk that is enclosed by this sphere, this pi r squared. So sigma pi r squared is the charge inside the sphere at the stage C. That's the reason why we have sigma pi r squared over epsilon 0. Number 6. Don't eat. It's not a bagel, but it looks like a bagel. We have charges inside and outside. This is a closed surface. Electric field flux passing this closed surface doesn't care any charges outside. You need to kill everything outside. It does contribute as long as they are inside a closed surface. It says that they are floating at the central level. Therefore, the contribution of total to B and C, they are the same, and sum of these must be the same as the contribution passing through the closed surface A. All right. Then, what is the answer? The net charge inside is -1. It is a 0. So charge Q over epsilon 0 is the total flux, and Q is -1 Coulomb. This is the answer for A. For B and C, because they are symmetric, just 1/2 of this is the answer. Trivial. Next, we have a uniformly charged surface. Electric field is this one, up and down. Okay. Flux passing A. This is A. This is N. If is parallel to E3, in that case, this surface has the flux pi, what is the radius? Pi r squared multiplied by electric field. Electric field is sigma over 2 epsilon 0. Pi r squared sigma over 2 epsilon 0. However, we have rotated this side, rotated this about the y-axis by an angle of theta. Electric field is along this direction. This one makes the angle of theta. Therefore, we have additional directional cosine theta. Next, we have B. Oh, B has a strange shape, but don't worry. A and B share the same boundary. Same boundary. Haha. So you don't have to compute it. You just copy this result. By the way, this direction is upward. This direction is downward. Therefore, the answer in magnitude is just the same, but the sign should be flipped. You have negative sign. Everything else are the same. The flux passing the whole closed surface of the cone, it's a zero. Why? Rho equals a zero inside the cone. No charge. Q over epsilon zero. Q is a zero. Number 8. We have a line charge, uniform line charge with charge density lambda. Evaluate the electric field flux passing each of A, B, and C. Okay. First, A. Just think about this surface. This one shares this and this and the remaining piece, A, B, and this rectangle, they share all of the boundary. But we do not want to evaluate a complicated surface integral. Instead, if you are clever enough, haha, you will find a cylinder that shares the rectangle. Understood? We can draw a cylinder with the radius, some radius, to the tangent, this radius. And then electric field flux, you will find lambda times L is the charge, Q, contained inside. And because of the symmetry, if you look at it on top of this figure, you have angle theta, and the whole angle is the 2 pi. And electric field flux is Q over epsilon 0 is penetrating the whole surface. However, among them, because it is a uniform, only theta over 2 pi penetrate this surface. This surface. Okay. This charge is lambda h. Therefore, the amount of electric field flux passing this surface is this one, and that is the same as the flux passing B, but A's direction is toward the charge, so we have sign difference. We have to put the negative sign on it. So first of all, it looked very complicated, but it was actually a trivial problem. Number 9, what happens the case if we have a uniform charge? Okay, the uniform charge distribution, we have sigma over 2 epsilon 0 along both sides, uniform electric field. Okay, then E times perpendicular to the electric field compute the cross-sectional area. They are given in here as shown in the. Again, we have a sign difference for A and B because the normal direction of A and B are in opposite sense. Finally, 10. Two large identical parallel plates are. We have a plate. This is exactly the same as the previous last question in the previous class. So let me pass all these things. What you have to remember, if there is a sigma, it is sigma over 2 epsilon 0, sigma over 2 epsilon 0. If you have a minus sigma, it is toward this direction. Therefore, we have sigma and minus sigma. The electric field is isolated between the two plates, and outside sum cancels. This is the parallel plate capacitor.